Biochemical reaction, like any chemical reaction, always proceed toward equilibrium. That is, to a state where there is no net change in the concentration of the reactants. Now, if we look at a reaction coordinate diagram, we can easily determine whether or not a reaction is spontaneous. In our case, the free energy of the product is lower than the free energy of the substrate, which means that the reaction is spontaneous. Or in other words, the change of free energy between the product and the substrate, delta G prime naught, is negative. And that is determined by thermodynamics parameters. Now, external factors can also affect the equilibrium. For example, the rate of consumption of the product in a subsequent reaction will change the equilibrium. Both these external factors and the thermodynamic parameters can tell us something about the spontaneity or the directionality of the reaction, but cannot tell us anything about the speed at which the reaction proceeds. The speed of the reaction is determined by the catalyst of the reaction. Biological catalysts will increase the rate of the reaction by 5 to 7 orders of magnitude. In most of the cases, biological catalysts that are called enzymes are proteins. However, there are some cases where the enzyme is made of RNA, ribonucleic acid. For example, the reaction that stitched together amino acid during the synthesis of a protein on the ribosome is catalyzed by ribosomal RNA and not by proteins. If we take an example of a reaction, for example, the first step of glycolysis, where glucose reacts with ATP to form glucose 6-phosphate and ADP, this reaction is catalyzed by an enzyme called hexokinase. Based on the change of free energy, which is minus 16.7 kJ per mole, this reaction is known to be spontaneous. Now, imagine that we have in a test tube a specific concentration of glucose and a specific concentration of ATP, and if this reaction relies solely on the random collision between glucose and ATP molecules, we can estimate that the rate of the reaction in this case will be 10 to the minus 13 mole per liter per minute. If we add to the mix, not changing the concentration of glucose and ATP, if we add to this mix the hexokinase, then the rate of the reaction becomes 1.3 10 times 10 to the minus 3 moles per liter per minute. The reaction will be 10 billionths time faster in the presence of the enzyme than in its absence. Now, if we look again at the reaction coordinate graph, we have a spontaneous reaction because the free energy is lower for the product, is lower than the free energy for the substrate.
Why do we need an enzyme if the reaction is spontaneous?
Don't be fooled by the term spontaneous. It just means that you have a favorable reaction that proceeds from a high free energy state to a low free energy state. If you look at the reaction coordinate diagram, you can see that to go from substrate to product, you need to reach an intermediate state that has a high free energy. So you have an energy barrier that needs to be overcome for the reaction to proceed, for the substrate to be converted into a product. This activation energy is needed because there is bonds that are rearranged, there are transient charge that are formed on the enzyme, you have a distortion, a change of the position of chemical groups, and so on. So, in fact, it's the amplitude of the activation energy that determines the rate of the reaction. The higher the activation energy is, the slower the reaction will be. What an enzyme does, It first reacts with a substrate to form an enzyme-substrate complex. Then the substrate is converted into a product, and you have formation of an enzyme product complex. And finally, the product is released. You have formation of an enzyme-substrate complex and an enzyme product complex, as well as other intermediate of the reaction. You have, for example, the transition state. All of these complex, all these intermediate of the reaction, are stabilized by the enzyme, so they have a low free energy. And as a consequence, the activation energy in the presence of enzyme is reduced. And when the activation energy is reduced, then the reaction will proceed faster. So that's how an enzyme can accelerate the reaction